All right, Matthew, here we go. We've got lesson 3.1.1, sample space. All right, so sample space is all of the possible outcomes for a situation that we're doing with probability. So all the different things that can happen. That's what sample space is. So in 3.1, we've got a table here. So this is one way to show sample space. And we're looking at people who can roll their tongue and people that can bend their thumb. Most people, well, a lot of people can like bend their thumb like that. So their thumb kind of goes a little bit backwards. That looks a little bit freaky. But anyways, so some people can do that. Some people can't. It's all about genetics. So we're going to assume that half the people can bend their thumb and half can't. And that half the people can roll their tongue and half can't. So we're going to look at this and fill in the table and find out what the probability is that some can do both. So if we're looking at the people that can bend their thumb, half of them can. So if we want to find somebody that can bend their thumb and roll their tongue, these two things have to happen at the same time. So I've got a 1/2 possibility and a 1/2 possibility. And since they're happening at the same time, we would multiply these two probabilities together. And we would get 1/2 times 1/2 is 1/4. Or 0.25 or 25%. And then if I got half the people that can bend their thumb and half the people can't roll their tongue, then that would also be 1/4, giving us a 0.25 or 25% chance. And same thing for this one. Can't bend their thumb, can roll their tongue, 1/4 again, 0.25. And then no bending thumb, no rolling tongue, 1/4 of the people would fall in that. So everything still adds up to 100%. I got a quarter of the people can do both. I got a quarter of the people can't do either. I've got a quarter of the people can do the tongue but not the thumb. And I've got a quarter of the people that can do the thumb but can't do the tongue. So it all adds up to 100%. And when we do our probabilities, the sample space should add up to 100%. All right, so what is the probability that somebody can do both? Well, here's the people that can do both, 25% or 1/4 or 0.25 as a decimal or as a percent, that's 25%. What is the probability that someone has only one of these traits? So maybe they can bend their thumb or they can roll their tongue. So they only have one trait. So these people right here can bend their thumb, but they don't have the trait for rolling their tongue. So that would be 1/4. And then over here, I got these people that can roll their tongue, but can't bend their thumb. So I've got 1/4 there. So we have two possibilities. This possibility here is the probability of, what did we say this one was? Bending and no roll. Whereas this one right here, this is the probability of no bend and being able to roll. So if we're looking to combine probabilities, we don't multiply now. Now we just add. And we get 1/4 and 1/4 is 2/4 or 1/2, which we could write as a decimal of 0.5, or we can write as a percentage of 50%. So once we have our sample space, if we're looking for multiple outcomes in this sample space, we would just add them together. All right, in reality, only 1/4 of the population can bend their thumb, and 7 out of 10 can roll their tongue. So we're going to make a new table to represent that. All right, so new table. These are kind of like in, was it like in biology class when you did the Punnett squares? If you took biology, you know, you did like, I think they're called Punnett squares. You did Punnett squares for different, what's it called? Like you might do it for like blood type or different genetic things, doing these Punnett squares. This is very similar to that. So here I've got rolling tongue out here, and I'm going to put it on the bottom here, bending the thumb. So we've got yes and no, yes and no. So this is yes, they can roll their tongue. This is no, they can't. This is yes, they can bend. This is no, they can't bend. All right, now the probabilities have changed in this one because in reality, only 1/4 can bend their tongue. So only 1/4 are yeses for bending, which means that 3/4 cannot bend the tongue. Over for rolling their tongue, 7 out of 10 can, which would mean that 3 out of 10 could not. And now we've got new probabilities for yes and yes. So now I've got 1/4 can bend and 7/10 can roll. So I would multiply those two probabilities together and get 7/40, which is, if you do your calculator, it's approximately 17.5-ish or so, or 0.175-ish. Or is that exact? I don't know. We'll just go with 0.175. Stupid announcements! All right, announcements are over. All right, so we're going to keep on doing this. Can bend but can't roll, 3/10 times 1/4. So that would be 3/40. If you break out your calculator, you'd find out that that is 0.075. Is that right? Yes. All right, now they can't bend, but they can roll. So this is 7/10 times 3/4. That comes out as 21/40. So I'm just multiplying 3/4 times 7/10. Remember, when you multiply fractions, you just multiply the numerator and the denominator together. So 7 times 3, 21, 10 times 4, 40. Last one, 3/10 times 3/4. That would be 9/40, which comes out to 0.225. Now, if you look at this, 7, 3, that's 10, 31, 40. So we got 40/40. It's still adding up to 100%. So there's our new table. Part B, what's the probability that somebody randomly selected can do both traits? That would be this section right here. We've got a 7 out of 40 chance of doing both, which is also written as 0.175 or 17.5%. What is the probability that a randomly selected person can roll their tongue but not bend their thumb? So they can roll, but no bend. That's 21/40. Or 0.525 or 52.5%. So about half the people can roll their tongue but not bend their thumb. I am both for yes. I can roll my tongue and I can bend my thumb. So I am the rare occurrence. Actually, this is the most rare occurrence right here, not being able to roll your tongue but being able to bend your thumb. All right, people from the Navajo Native American tribe either have type O or A blood. So they don't have type B blood if you are 100% Navajo. So we're going to look at the probabilities here. So let's see, 73 out of 100 have type O, so that's 73%, and 27 out of 100 have type A. All right, suppose two individuals from the Navajo tribe were chosen randomly. Find the probabilities for the combination of blood types they would have. All right, so we got two people here. And we're going to look for the combinations, and this is our sample space inside here. So the sample space is going to have two different people in it, and the combinations of those two people. So This is going to be person number 1, and this is person number 2. So Navajo person number 1, Navajo person number 2. They have 2 possibilities. They can have A blood or they can have O blood. That's person 2. Person number 1 can have A blood or O blood. Okay, now it says that each person has a 73 out of 100% chance, or 73 out of 100 to have type O. So O would be 73 out of 100. And this O would be 73 out of 100. They both have the same chance of having O blood. A blood is 27 out of 100. So if you're picking 2 people, that's our situation here. We're going to pick our first person and then our second person. The sample space would be they both have A. Person 1 has A, but person 2 has O. Person 1 has O, but person 2 has A. And then this is they both have O. So those are the 4 outcomes when we have 2 people from the Navajo Nation. A and A blood, A and O blood, O and A blood, or O and O. That's our sample space, our outcomes. All right, so if we multiply 27 over 100 times 27 over 100, it's probably easier to do this as a percentage. So 27 times 27 over 100 over 100. If we work it out, it comes out to 53.3. Oops, wrong one. That's this one. 53.3%. For A and A, it's 7.3%. Wow. If I do 73 over 100 times 27 over 100, it comes out to 19.7%. And this one is also 19.7%. What is the probability that 2 Navajo people both have type A? That's right here, 7.3%. What is the probability that they both have the same blood type? Well, that's 2 different situations. They can both have A, that's 7.3%, or they can both have O, which is 53.3%. So if we're taking 2 different parts of our sample space and we want to know what they are combined, we would just add these 2 probabilities together, and that would come out to 60.6%. All right, backside. Let's flip this over. There we go. All right, Zach and Nick are shipwrecked on a desert island. Oh no. Zach has been injured and needs a blood transfusion. In most populations, 45% of the people have type O blood, 40% have type A, 11 have type B, and 4% have AB blood. All right. Make a probability model representing the blood types of Zach and Nick. All right, so here we've got all of our percentages. Remember, 45% is 0.45. So what's the probability that Nick and Zach both have O blood? So that would be 0.45 times 0.45, which is 0.203. And I'm just going to give you the answers here. This is going to be 20.3%. So I just did 0.45 times 0.45. So Nick and Zach both have O blood. What if they both have A blood? That would be 0.4 times 0.4, which is 16%. What if they both have B blood? 11% times 11%. So that ends up being 1.2. It's actually 1.21, but 1.2%. I'm rounding to the nearest tenth here. And then 0.4 times 0.4, I'm rounding, of course, and this ends up being 0.2%. It's actually 0.16%. It's 0.0016, so we're rounding it to 0.2. And then filling in everything else, 0.45 times 0.4 is 18%. And that's going to be the same thing as this one because it's 0.45 times 0.4. 0.45 times 11, 0.11 is 0.05-ish, so that's 5%. And then this one is also the same, 5%. 45 and 4, that would be 1.8%, which comes out to 0.018-ish, about that. And then this one's the same over here because it's 0.45 times 0.04, sorry. Let's see, B and A blood, 0.4 times 0.11, that would be 4.4%. And here's A and B again, just with a different combination with Nick and Zach instead. So this is 4.4. Then we've got AB blood with A blood, so 0.4 times 0.04. That comes out to 1.6. And it's the same over here. Here's A blood and AB blood, 1.6. And then our last one, AB and B. So that's 0.04 times 0.11. And that comes out to 0.4%. And this is the same thing, B and AB. So 0.4%. All right, so that is a probability model of the blood types for Zach and Nick. What is the probability that Zach and Nick have the same blood type? Well, here they both have O. Here they both have A. Here they both have B. And here they both have AB. So we're looking for all of our sample space where they have the exact same blood type. And these 4 spaces are where they have both OO, A and A, B and B, AB and AB. So we would add up all those parts of our sample space. So if we add all those numbers together, there is a 37.7% chance that they have the same blood type. Luckily, 2 people do not need to have the same blood type for a transfusion. The chart to determine the probability that Nick's blood is compatible with Zach's is right here. So O can be transfused into anybody. A can be transfused into A or AB. B can be transfused into B or AB. And AB can only go with AB blood. So Zach's injured, so he's the injured one. And Nick is healthy. So we want to know if Nick has O blood can go into AB blood, A blood, or B blood. So all of this column would work. So 20.3, 18, 5%, and 1.8%. So if he has O blood, he can go into all of these. Now if he has A blood can only work with A and AB. So 16%, here they both have A. So if Nick has A blood, he can give it to Zach if he has A blood, so that's 16%. And if Zach has AB blood and Nick has A blood, he could give him that blood. That sounds pretty gruesome. All right, for B blood, if Nick has B and Zach has B, he can give him blood. So B and B is 1.2. And then B and AB, because B can go into AB. So if Nick is B and Zach is AB, that would work. Lastly, if Nick has AB blood, the only thing AB blood can give to is another AB blood. So 0.2. So those are all of the outcomes where Nick has blood that can be given to Zach. O blood, all of them works. If Nick has A blood, he can give it to Zach if he has A or AB. If Nick has B blood, he can give it to B or AB. And if Nick has AB blood, then Zach's in trouble because he can only give it in that situation. So if we add all of those together, there's a 64.5% chance that they are compatible together. Better than average, but looks like it's better not to be on a desert island. Blood type is affected by genetic inheritance. What if Zach and Nick were related to each other? Would that have changed the outcomes? And yes, the outcomes would have changed if they're related. Because if they're related, then their parents are the ones who give them the O's and the A's. So they have a better chance of having blood that is, what's it called? Compatible with each other. So yes, this would be better because the outcomes that we did up here were random. Meaning they were independent. But if they are related, then they are dependent because the relation means that they're more likely to be connected together by blood type because they have the same parents, so they're more likely to get compatible blood. That's usually why if somebody is injured, they look for a relative to give them blood because they're more likely to have compatible blood types. The outcomes were independent, but related people would be more likely dependent. What must be true in order to assume a probability error model will be given an accurate theoretical probability? That's kind of a weird thing. And here's what we're saying. If this is a accurate sample space of what we're doing, we have to assume that one thing is not affecting the other thing. So we can't assume that, well, we're assuming that Nick's blood is not affecting Zach's chance of getting the same blood type. So we're like the whole thing about being related to each other. We're assuming that one is not affecting the other, that they're independent of each other. So we must assume that they are independent. And we would say the events are independent. That's all I got. Math hard. See you later. Bye-bye.